Good morning to Montgomery Elementary School. It's a beautiful day in the neighborhood, as they say is Mr. Rogers still on PBS? No, he's not on PBS anymore. Anyhow, my name's Wayne Fagan, and I'm chair of D. Howard International Education Foundation. And we're delighted to present today a virtual presentation, an opportunity for you to speak with Mr. Jonathan Binkley, who is Senior Project Leader, Engineering, long title, Engineering Program Management and Systems Engineering at our good friends, the Aerospace Corporation. And this is being presented by, we use the initials DHEDF and our good friends at UTSA Cleese College of Engineering and Integrated Design. And we have with us, representing UTSA Cleese College, Carlos Velez, who will introduce himself shortly, and he will be your moderator. And then we also have Mr. Binkley with us, and he will be your presenter, and you'll get a chance to speak with him in a few minutes. And then we also have Leanne from Aerospace Corporation, along with two of her colleagues. None of this would be possible without this whole crew, including, most importantly, Montgomery Elementary School, and we're so delighted to be with you. So, Leanne, if you'd like to say a welcome on behalf of the Aerospace Corporation and introduce your colleagues, and then we'll turn it over to Carlos.
Okay, well, it's an exciting day here. I'm Leanne McGinley, and I'm with Lauren Gandera and Rebecca Kim, and we're on our K through 12 STEM outreach team. And we're so excited to be here. This is one of our favorite things to do, but I don't want to take up the time, so I'm going to turn things over to John Binkley. And
Well,
we're with the Aerospace Corporation.
we'll let Carlos introduce himself, and then
Oh,
he'll
yeah, sorry,
introduce.
Carlos.
It's
I'm
like,
so sorry.
no, totally
Okay.
okay. Just
All
yeah,
right.
I'll keep it quick as well. But yeah, just wanted to say a big welcome and thank you for having us here and letting us present to you. Also, my name is Carlos Velez. I work here at the University of Texas at San Antonio within our Student Success Center for Klesse College of Engineering Integrated Design. So we get to work with architecture students, engineering students, construction students, and so we like to do these kinds of things because in order to train students and get them into these fields where we educate them and teach them how to get into these careers, first we have to get you all interested and understand that this is an opportunity for you all to be able to engage with. And so we're excited to show you these kinds of things, and hopefully in the future you're interested in this presentation, you like some of the topics that we cover, and then you see yourself in these roles in the future, and this is a path that you'd like to go down. And so excited to be here and do that. And so with that, we'll go ahead and pass it over to John. But before I do that, I'm just going to say one thing. So today we're going to have our presentation. We'll have some time for questions at the end. So as we're going through the presentation, think of some questions or think of some things that might be interesting for you. We're also at the end going to have some roles for you all to play where you will take the role of doing a rocket launch yourself. And then uh, we'll have some questions at the beginning as well. So we'll try to keep this as interactive as we can for you all. But with that, John, I'll go ahead and pass it over to you and take it away.
Yeah. Oh, hello. Gosh, it's great that you're coming out here and seeing us today. Yeah, like I said, my name is John Binkley, and before I get into my talk, I'd just like to give you a little bit of my background. And I'll start when I was a fourth and fifth grader. I was pretty good in math, and I like to clarify that. I mean, I worked hard in math, and I got good at math. It wasn't that math was just handed to me and put into my brain. I really had to work hard to do to do well in math. And so I was doing real well up until about high school. I got kind of detoured, and I decided I wanted to become a car mechanic, which is a little different, but and I did that for a few years, probably about three or 4 years. And I was doing an oil change one day on a hot day, and oil was dripping down me, and I thought, there's got to be something else out there for me. And you could probably understand that. You guys, San Antonio is very hot, and I was working in Downey, and I thought, it'd be better if I was designing these cars instead of working on them. And so that was my motivation for going back to school. And I was very, I did very well. I was a little bit nervous when I was going in there because I had taken 3 years off, but I worked very hard. I worked, I did, and I did not want to go back to changing oil. And so that was my motivation right there. I wanted to exceed in this, in school so I can get a degree and advance my career. And so sure enough, I did graduate from college. I got a degree in mathematics and statistics. And then later on, I got accepted into a program at UCLA. Has anyone heard of UCLA? Any of the students? Okay, UCLA. Well, it's probably the best college in the world. People will disagree with that, but it stands for University California, Los Angeles, and it really is a great school. And I was a little bit nervous again. I felt like, God, this is one of the better schools in the world. It's not the best school in the world, but it's one of the better schools in the world, and I'm going to be competing with all these people trying to get a master's degree. And so, what do you think I did to exceed there?
Leon, you want to come up and answer right here? Come on. So what do you think you did?
So I think you worked hard and you paid attention and you gave your best efforts.
Excellent. Excellent. Exactly. Number one, I worked very hard. I tried to stay as focused as I can. I mean, I know that's hard. You get a little fidgety, but I tried to stay as focused as I can. And I did really well, and I got my degree, master's degree, and I started working at the Aerospace Corporation, and that's where I work right now. But I've been here for probably 35 years, and I've had a lot of different jobs. I did some reliability and statistics. You'll be taking that class later on, and I also worked on a rocket program where I was actually helping build the rocket. It was a Delta IV rocket. And at the time, the Delta IV Heavy was the biggest rocket we had in the United States. So that was really exciting. But probably my best job was I was director of a launch center. And that's where our engineers go and give the go or no go during a launch. And if they give a no-go, we don't launch. So if there's a problem with the rocket when it's during the countdown, or or we're filling up the rocket and there's a leak, or the weather's bad, we will have to cancel the launch for the day. And we call that scrub the launch, which means just canceling the launch for the day. And we will try to do it tomorrow. And so I ran that center to allow us to make those decisions. And those are big decisions because you could have, there's two errors you can make. One error is you can say there's a problem with the rocket and we should not launch today. And let's say there was no problem with the rocket. We just misdiagnosed it. And so that's a mistake. We held the launch. We said we're not going to launch today when there was nothing at all wrong with the rocket. The other mistake and is much worse. And we say the rocket's fine. It looks great. There's all the signals are great. The weather's great. Let's launch this rocket. And there's a problem with the rocket. And we just didn't catch it. We did not see it. And we lose the rocket. And I'll be actually showing you a video of some launches where they didn't go so well. So that's an exciting video. But so that's we can never ever we're going to launch the rocket, but we can never get the risk of launching the rocket down to zero, or we would never launch the rocket. So there's always going to be a small chance of having a problem. And we want to get that number, that small number, as small as it can be. So that's what I've been doing. And let's go to this chart right here. And this is just a little demo of the different ways we use space. And here we have in the one corner, you see the globe with the satellite and the ship and the plane and the person that looks like a soldier. Well, the plane wants to communicate with the soldier. He wants to talk to them. Let's say they're soldiers. They're doing an exercise. but signals, the voice signals cannot go through the Earth. So what they have to do is they have to send those signals up to a satellite that's way up there. It's 24,000 miles above Earth. And it has line of sight with both the airplane and the soldier. So they can send a signal up. The satellite will relay that signal down to the soldier and they can communicate. So that's a very cool thing that we do, and the communications are typically very secure, so someone can't listen in and understand what we're saying. Another way we use rockets is through what we use satellites for is we got the charts. Oh, there he is. For predicting weather, and you see that looks like a hurricane. That's taken from an imaging satellite. So does anyone know why is that important? Why do we want to predict weather? What's the
Why would we
purpose
want
of
to
that?
the 9?
Think I might want to predict weather because maybe if it's not a good time to go, then maybe like if it's not like a good weather, then y'all might not want to like go because it can be like a little storm in the little I forgot what it was.
Well, that's great. That's great.
Where can maybe become destroyed. So I think that would not be a good idea.
That's great. Mrs. Baldwin, you got a very smart class. Thank you very much. Yes, we want to be able to predict weather if we decide we're going to take a boat out. We're going to take a cruise. We're going to get in our boat and there's a hurricane out there. That's a image of a hurricane. We might run into a problem. We might run into a big problem. And so we predict the weather, and also we use that during a launch. We want to say, if there's a launch and there's bad weather coming, we're going to put the rocket away. We literally do that, and we'll wait for another day. So predicting weather is very, very important for safety of people and how we use it. To the right, we also have another application of space is the GPS. And does anyone know what we use GPS or what GPS stands for?
What GPS stands for?
Yeah, what GPS or how we use it. Either that or how we use it.
You want to take a guess, Elsie? You want to come up here and take a guess? So 3 letters, GPS. Take a guess. What about over here? You want to come take a guess? Okay. Yeah, you can come up here so they can hear you. So 3 letters, GPS. What do you think it stands for? And you can talk into the camera. They can see you. Google, but last word S, last letter S. So Google picture.
I'll give you a clue. Global.
Maybe picture. And then S. What do you think it could be?
All right. Well, it stands for, I'll go ahead and say it. Oh, wait, stay up there, though. Stay up there.
Wait.
Come back. It stands for Global Positioning Satellite. And how do you think we use it? How do you
think
why do we need GPS?
To find where you're going.
Oh, excellent.
To find where you're going.
Yeah.
Yes.
Good job. Yeah, to find out where we are, where we're going. It predicts your exact, not predicts it, it calculates almost your exact location on Earth. And so it's amazing. It's, absolutely amazing technology. And that's something that probably you have on your cell phone. You use it probably every day and you may not realize it. So we also use satellites to look at different constellations and look into planets in space. We have a picture right there of a photo of taken from the Hubble satellite of Saturn. Now we have telescopes. Basically, it's a telescope in space. Now we have telescopes on land, and I guess my question is, and they work pretty well. Why do we need telescopes in space? I mean, we already have them in land. Why do we need them in space?
So why do we need telescopes in space?
I think we need like telescopes in space to like see planets and like see how stuff is developing in space and like try to see like aliens and stuff.
I guess my question is, though, we have telescopes on the ground. What's the purpose of putting a telescope in space? Why is that so much better
Like
to
see
put a
more
telescope in space?
to see like more above Earth and like above like where we are, like so you can see more in
Oh,
space.
okay. Yes. You can get around a little bit more. You could take, different images. Probably the biggest advantage of putting a telescope in space, though, when you have a telescope on ground, when you look at various objects, that light has to go through the atmosphere. And this atmosphere we live in, is great for living conditions. But when light goes through it, it gets blocked. Some of the light waves get blocked. And so you see it comes out not as clear. And then when you put a telescope in space, you don't have to go through the atmosphere. We're in what we call a vacuum. We're in space. It's very, very clear. So we can get excellent images like that. And so now if we point that telescope, instead of looking at an object in space, we point it at the ground. We look and we see that image right there. You see that football field, and that's an image taken from a satellite pointing at the ground. And you guys have probably seen that on Google Earth. And you could zoom in pretty far. You could zoom in. You could almost see. You could definitely see cars. This is not zoomed in, but you can see blocks and houses, and if someone has a swimming pool in their backyard, you can find out who that is, and so on. So it's it's really great technology. Another and to the far right we have that image, and you see that little yellow band. That's measuring carbon monoxide, and this is a satellite called the Ares satellite, and it measures different kinds of gases in our atmosphere. And we're monitoring our Earth is changing, and we want to make sure that we want to look at the different gases we have in our atmosphere to see is it getting bad? Is it what actions can we take to slow down the acceleration of elements that we have in the atmosphere. So right there, that's like I said, that's measuring carbon monoxide, and actually is used in this case to detect fires. And there is a great big fire. This was in 1995 in Indonesia. And you can see that to the right. You can see that image where it's really red. That was taken from the satellite. And so we can actually estimate forest fires, where they are. But it takes a little while to do that using this old technology. It might take a day or two, which is I'll be talking about that in a little bit, but that's a long time to wait till we detect there is a forest fire. So keep that in your mind. Okay, so the next question is, how do we get satellites into orbit? And so if I threw, let's say, a baseball, and I threw that baseball as hard as I can, let's say 100 miles an hour. Probably, I can't throw a baseball 100 miles an hour, but let's say I throw that baseball 100 miles an hour. Can I put it into orbit? What will happen? What forces are acting against that baseball? Why can't I put that baseball into orbit?
Joe? The question is why, if he threw that baseball, why would it not go into orbit?
Yeah, it's just going to go a little ways and then land on the ground and roll a little bit and stop.
What do you think?
Because of the gravity will bring it down.
Excellent. Gravity is pushing it down. Now we have one more force acting on that baseball. When we throw it, gravity is pushing it down. There's something else that's happening, though. When you throw that baseball in the air, it starts slowing down. And that's because does anyone know what force is acting on that baseball, why it's slowing down? Gravity is pushing it down, but why is it slowing down?
So the question is gravity is pushing it down, but what else is slowing it down? What do you think? You want to talk to the camera so they can see?
It's going to happen is the other is um,
Oh, I think oh the gas in the air.
Oh, excellent. Excellent. Right? That's spot on. Spot on. The gas in the air, the air pressure. Like when you're going driving down when your parents are driving down the road and you stick out your head out the window, you feel a lot of air pressure. Well, when I throw that baseball really hard, air pressure is acting on that baseball and it's slowing it down. And so we got a problem. If we want to put satellites on Earth, we got two things acting against us. We got gravity pushing it down, and we have the gases, the air pressure on Earth that is actually slowing the baseball right when I release it. It's slowing that baseball. So what I'm going to do is I'm going to have to pretend here. And you see that little picture of that baseball player, and he's on a big tall mountain, and that mountain is 100 miles high. Now, there are no mountains 100 miles high on Earth, but let's just pretend there is. And now up there, 100 miles high, there's very little air. There's very little air pressure. There's very little gas. We're almost in what they call a vacuum. There's just not much gas, not much air pressure at all. And so air pressure is not going to be slowing that baseball down anymore. But we have that pesky gravity. Still, it's going to be pushing that baseball down. So I'm on top of this 100-mile mountain. I throw that baseball as hard as I can, 100 miles an hour. It goes a little ways because air pressure is not slowing it down, but then gravity pushes it down. And you can see that V1 right there. It lands a little ways away, but it certainly doesn't put it in orbit. So what I have to do is I hit the weight room. I start lifting weights. I get real strong. Instead of throwing it now 100 miles an hour, I can throw it 500 miles an hour. And so I throw that baseball as hard as I can, and it's going a little bit more further because I'm throwing it harder, 500 miles an hour. But that air pressure, that gravity again is pulling it down. You can see that at V2, where the satellite is being pulled down by gravity. So then really I have to go hit the weight room again, lift more weights, get stronger, get stronger, get stronger. And now I could throw 17,000 miles per hour. And I throw that baseball, and you can see that V3, and it goes around, and the gravity is still pulling it down. But gravity is pulling it down at the same rate as the Earth curvature. And so it actually goes into orbit. If I can throw it with no air pressure, 17,000 miles per hour, gravity is still acting on the baseball, but it's actually going to be staying in orbit. It's sort of like if you put a ball on a string and started throwing it around, you spin it around. Gravity is my hand pulling it, but it continuously spins around. So now we don't have. Well, we got two problems with this. One is I'm not sure if I could throw 17,000 miles per hour. What do you think, class? Just do you think I could throw it 17,000 miles per hour? Yes. They're going to say, if there's a prize in it, I'll say, yes, you can. Yes, come on up.
Oh, someone that said yes.
Yes, I can throw 17,000 miles per hour. Okay, well, in reality, okay, all right. So, I can't throw 17,000 miles per hour, and there are no mountains 100 miles high. So we have a problem. So next slide. So we have to do something. So what we do is we rely on very powerful rockets. And rockets use Newton's third law. And that means for every action, there is an opposite reaction. And maybe you've heard that, maybe you've not. And maybe you've seen that. I know you've seen that demonstration in a balloon. If I blew up a balloon, and Mrs. Baldwin, do you happen to have a balloon? Does anyone have a balloon?
I do. I have two.
Oh, all we need is one. Can you blow it up real quick and hold it?
Sure.
Okay, go ahead.
Okay.
She's really working hard.
So hard.
All right. So, okay. So she's not going to do it yet, but when she releases that balloon, you're going to see air come out. Air is going to come out the one nozzle into the balloon, and that's the action. What's the reaction? The balloon shooting off in the opposite direction. So go ahead and let's see if that works. So air is going to be coming out the nozzle in one way. The balloon's going to be shooting off in the opposite way. All right, I think you got it.
Okay.
Anytime you're ready.
Let it
5,
go.
4, 3, 2, 1. Blast off. All right. So you saw that, like I said, air was coming out that nozzle and the balloon was shooting off in the opposite direction. We use that exact same theory for launching rockets. We have, in this case, we have the nozzle, we have propellant, and I got a model of a rocket engine right here, you can see. Propellant is coming out this nozzle, just like the balloon, but a lot of propellant is coming out. It's coming out thousands of pounds per second, and it's coming out very fast, close to 10,000 miles per hour. And that's the action. All that burnt propellant coming out very fast. The reaction is this rocket taking off in the opposite direction. So you can see that's really how we do it. We have to have very powerful rockets because no one can throw it 17,000 miles per hour. So the first thing we need to do is we need to get the satellite out of the atmosphere because, like I said, all that gas and all that air pressure is going to slow that rocket down. So the first thing we do is we have to have very powerful engines to get that rocket out of the atmosphere. And then we give it that's step 1. Step 2 is to give that 17,000 mile an hour push, and the rocket does that too. So the rocket's doing 2 things. It's getting the rocket out of the atmosphere into a close vacuum, and then making a maneuver, and then giving that big 17,000 mile an hour thrust to put it into orbit. Next chart. Okay. Rockets typically have 2 parts of them. The main parts are the first stage, and that's the first stage of the rocket. I wish I could point that out to you, but that's those 3 little boosters on the bottom. You say where they're marked boosters. That's the first stage. And that part of the rocket is really, its main purpose is to get the satellite rocket out of the atmosphere. And then we have a second stage. And you see there, Delta cryogenic second stage. And that's the part that puts the rocket, gives that rocket that 17,000 mile an hour push. Now, its whole purpose is to put that spacecraft into orbit. And I got a little model of a spacecraft. And these are its solar arrays right here. And it unfurls the solar array. So the whole purpose of this big rocket, this rocket's about the size of a football field. And this satellite's only about the size of a car. So the only purpose of that rocket is to put this satellite into orbit. And so it's a lot. I mean, it has to be very big and powerful in order to do that. But people want to know how on earth do we put this satellite into orbit? This thing still weighs about 10,000 pounds. So the satellites have to be very, very powerful. And I undid the solar arrays here. You guys, I don't know whether you can see them right here. And what do you think the purpose of solar arrays? Why do we put solar arrays on satellites in orbit, on space?
You think, Elizabeth? So what do you think the purpose of the solar array? Yeah. Well, tell them.
Solar rays is to hit the little.
So think about it, solar
Panels.
Uh-huh.
And then when the sun rays hit it, it can give off energy.
Okay, so when the sun rays hit it, it gives off energy.
That's excellent. That is excellent. Yes, the sun rays will hit these solar panels, give it energy to charge up the batteries. And so we can keep these things up there for years and years and years. And this technology, solar arrays, was developed with rocketry. It was developed, how are we going to we're going to put a satellite into space, and we need power in order to power the telescope and to do various things. But where are we going to get the power? We're going to get the power, the energy from these solar rays. Like you said, the sun's going to hit it, and it's going to produce energy to charge the batteries, to keep the batteries continuously charged. And these solar arrays will last 15, 20 years. And we've had satellites in orbit that have lasted a long, long time. So next chart. Okay, so I wanted to talk just a little bit about where we launch. There's 2 spots, actually 3 spots in the United States where we launch. And if you see Vandenberg, SFB, it's Space Force Base, and that's in California. And there we can launch satellites going down. If the satellite needs to go down, we can launch it. We can't launch satellites from Vandenberg Air Force Base over the United States. And why can't we launch over the United States a rocket?
Why do you think we
Why
can't launch?
do you think we have to launch over water?
Samuel? No. I was trying to. Angel? So why do you think we can't launch rockets over the United States?
Maybe because it will burn some stuff.
Okay, because it'll burn some stuff.
Yeah. Yeah, parts are actually falling off the rocket. And also, if there is a problem with the rocket and it explodes, it's going to be over populations. So we always launch rockets over the ocean. And you can see the other spot we launch is from Cape Canaveral, Florida. And most of the launches are there. Probably 70% of the launches are there, most of them. And they're always the launches, it's called due east. They're going, and there's another rocket, you can see that's where we launched the Starship. And that's on the in Texas, and it's very narrow where we can launch that because we don't want to hit Florida. We don't want it to go over Florida. We don't want it to go over Cuba. So it has to go really, really thin where we can launch. Okay, so next chart. Okay, so I'm going to show you a video now. And this video is what happens during a bad day. When we like I said, we can never get the risk down to 0. We always are going to fly. We're always going to launch. There's always some risk that there's going to be a problem. Now, back in the days, this video was taken in the 60s and the early 70s. This was a long time ago. We really didn't have the technology in order to launch rockets with a lot of reliability. And so we ended up having a lot of failures. And all these launches, there was no people on board. So no one got hurt in making this video. So let's go ahead and roll it.
-8. -6.
So you saw all those launch failures, and so there really are devastating. I've supported, well, probably hundreds of launches, and I've had two failures. And each one of them, I knew all the work that had to go into building that rocket and the payload. One was going to the space station. It was going to replenish food and some experiments to the astronauts on the space station, and they had to pack it. And it was devastating to see that rocket blow up. And another one blew up right on the pad. So they really do hurt your stomach to see that. But like I said, no one was hurt in the making that video. And so my question to you is, what can we do to improve the launch reliability? How can we make the rockets more successful? Well, if you were in charge of all space, what would you do? What actions would you take to make launches more successful?
So what could we do? What's one thing we could do to make the launches more successful?
Maybe y'all could like use less gas.
Well,
So
we have
like
to put, yeah,
go to
that's
the
yeah, that's a good one. We use less gas, but we have to, like I said, we have to get that rocket on ground. We have to get it through the Earth's atmosphere. We have to give it a 17,000-mile-an-hour push. That takes a lot of energy. It's going to take a lot of fuel. But yeah, we want to. That's the biggest problem is the fuel. That's what's blowing up. So, anyone else have any ideas on what you would do if you were in charge of space? What actions you would take?
Forever. So what else could they do to make sure that to prevent the failure of launches? Like the base of it?
definitely like the basic. You need the basic to fly it.
You need the base of the rocket? Yeah, we need that.
Oh
You
yeah,
gotta have that.
yeah. You need the
What
base
else
of the
do we-
rocket. You need the rocket to hold up, to
Yeah,
be able
we
to
need the
stand on
base
its
of it.
own.
What else? What else? Let me do one more.
And I'm going to
Cassie.
ask one more.
Okay. What else could they do to prevent the failures?
If you're in charge of all space, what would you do to prevent
Oh,
these failures?
say it one more time.
Maybe like check it more than once.
Check it more than once. Brilliant. Absolutely brilliant. Yeah, we have to check it a lot of times, and we do a lot of testing on the rocket, the very individual components. We test it and we test it again, and we do a lot of different checks, and we have a lot of different eyes making sure that the work that we do is correct, because every now and then people are human, they're going to make a mistake. So we have another person to check that, make sure that that there are no mistakes. And like I said, we can never get that risk of launch failure to zero, but we can get it as low as possible. And so anyways, but those are all excellent answers. So but I'm going to show you what we're doing, some of the exciting things we're doing in space. You see that astronaut right there? He's on the space station and he's unfurling a solar array. What I was just telling you about, one of these solar arrays right here. And think about it. He's doing what you call an external vehicle maneuver. He's out in the space. He's not inside the shuttle. He's out there, and he's tethered down. There's wires and cables making sure that he doesn't take off. But that's an amazing job to be able to do that. And each one of you, that could happen. That could be, and I guess it goes back to hard work. That astronaut, I'm absolutely sure that astronaut right there did a lot of hard work and to get into that position to be able to do that. But what a job, huh? Amazing. You see the Earth in the background. Absolutely amazing job. Next chart. Okay, another incredible thing we're doing. You guys have heard about asteroids, right? And asteroids orbit the sun. And we want to understand them because some of these asteroids are billions of years old. Absolutely, very, very old. And so it's funny, but when an asteroid comes, some of these asteroids actually land on Earth, and we changed the name. It's an asteroid in space. When it comes onto Earth and lands, it's called a meteorite. And it's so what we did was we landed a spacecraft on a asteroid. landed it there, and took some samples. And this asteroid, it had never been, all the meteorites that come on Earth are the Earth's atmosphere is going to kind of mess them up. It's going to age them. It's going to do some. They're going to be harder to study. But these asteroid samples were put in a vacuum, so we can take them back. And you can see that parachute on the right hand side. That's how we got the asteroids back, and they were able to track that periscope, tell us, coming down, and we were able to take the samples. So, and yeah, next chart. Another application that we did was we have that asteroid right there, and we had a spacecraft, and its mission was to slam into that asteroid. So can anyone tell me why on Earth we got this innocent asteroid orbiting the sun? It's not bothering anyone. And now we get the spacecraft into space, and its whole purpose is to slam into that asteroid. Can anyone tell me why? What's the purpose of that mission? Why would we want to do that?
But why would they want it to slam into the asteroid?
They want it to slam into the asteroid so then it can stop it from going to Earth and ruining it. Like, this is the asteroid, this is Earth. Yeah, that's the entire purpose of it, to make it not do this.
Excellent.
This is a no-no.
That's bad. Good. That's wonderful. Wonderful. Well, that particular asteroid was not a threat to Earth, but that's actually the exact same purpose. What we do is we experimented. We slammed the spacecraft into this asteroid, and we measured how far the asteroid moved. And the whole purpose of this, if we do have in the future an asteroid come into Earth and it looks like it's going to slam into Earth, is going to be a problem, we want to know how much force we're going to have to enact on that asteroid to get it out of that orbit. So, and we've had two big events, where asteroids have come, and one hit the Earth, and it really wiped out all the dinosaurs. So we certainly don't want that happening to Earth now. So that's the whole purpose of this experiment, and it's amazing that we have the ability to do this. And again, the whole purpose is to understand what we need to do, how much energy we need to exert on this asteroid to get it to move, to get it out of the way. Okay, now we have the ability, and this is again incredible, to land. The boosters used to land once they're used up the propellant, land in the ocean, and now they can actually land, come back to the launch site. They're actually these are actually going down. They're descending. We ascending when we sent them up, and now they're descending so we could reuse them again. Next. Okay, we got what we call a rideshare program. And if you have a satellite that your classroom has built, and let's say it's under 200 pounds, you can launch it for $500,000. And you can go on this webpage and you can basically reserve a ride. If you did this 20 years ago, if you had a spacecraft, you were going to spend a lot of money. Maybe you weren't going to be able to launch it at all, because military at that time, it was really military was launching satellites, and they don't want to take on any hitchhikers. If there's a problem with a hitchhiker, could bring down $1 billion spacecraft. So they say, you're going to have to find another ride up to space. But now we can go right online, get to this webpage, and like I said, we can say how big the satellite is, and we have smaller ones, and they're less costly, and this is where we come. So if again, the colleges have used this website to launch their spacecraft into orbit, which is really cool. Next chart. Okay, this is the James Webb Telescope, and right there on the right is a image taken from it, or a photo taken from it. It's called the Pillars of Creation. It's a lot of space dust and some galaxies, some stars, but incredibly, imaging clean satellites. Now you see the people on the left working on the satellite, and they're all dressed in you see the uniform with I guess they are uniforms. What they're dressed in, we call them bunny suits, because they kind of look like bunnies, white bunnies. And so why do they need to dress like that? Their hands are covered, their faces are covered. They got everything like that when they work on these satellites. What is the purpose of wearing those outfits?
Why are they dressed like that? Let's have them speak up.
They're dressed like that because maybe there's gas in the air that they're working with, so they don't want to be touching that or smelling them, or letting them be sick because of.
Yeah, that's that's one of the purposes. That certainly you don't want to be smelling some of that stuff. Another reason they do it is because if you touch, let's say just without a glove, you touch that satellite, you're going to leave, you don't think you are, but you're going to leave a little oil from your hand on that satellite. And that's no big deal. It's going to stay, that little oil is going to stay on the spacecraft. But when we launch that spacecraft and we go into gravity, that oil is going to come off. There's not gravity pushing that oil onto the surface. It's going to come out and it's going to turn into a gas. And we call it outgassing. And it can cause problems. It can cause big problems. That if some of those gas molecules that aren't supposed to be there could clog up a telescope lens and we can have big problems. So that's the main purpose of wearing those bunny suits. And they might look funny, but they're very functional. Next chart. Okay, so we have, people don't realize this, but we have thousands of miles of cable. This is underneath the ocean right here of cabling. And this is how we communicate. You've used this and you didn't even realize it when you're communicating and getting on the web page. And we have this going across all the oceans, going across the Pacific Ocean, Atlantic Ocean. And the Aerospace Corporation wanted to detect if someone tried to do some funny business and maybe blow one of these things up. We want to detect if there's any motion or there's any problem with these. So Aerospace has built detectors for these things to keep them safe. So next chart. Okay, we have very busy constellations. This is a constellation of satellites. The satellite right there is just one of those dots on the Earth, and it has an orbit that goes around the Earth. And there's a satellite constellation that has 6,000 satellites called Starlink, and it's for communication. And anywhere on Earth, you can use this satellite to communicate. And there's, like I said, there's thousands of these satellites. Next chart. Okay, to detect forest fires. And right now, Google is developing some satellites. And again, it's going to be a large constellation to be able to detect forest fires within 20 minutes. Right now, I think I showed you that one image, and it takes hours. It takes sometimes days. And right now, you can see if you want to detect a forest fire, you have to really wait till it's about the size of 2 football fields. And by that time, it's caused a lot of problems. With this satellite by Google, it's going to be, you could detect a fire about the size of a classroom, 5 meters by 5 meters. So if you look around, it's a lot smaller and we can get on it real quick and before it causes a lot of damage. This is going to change everything. We lose a lot of we lose a lot of firemen putting out these forest fires. They cause a lot of damage to our environment. They wipe out trees and everything else. So this is going to be amazing once this thing is up. It's expected that they're going to do their first launch, I believe, next year. But the full constellation would be about 50 satellites in a low Earth orbit for detecting these forest fires. Next chart. All right, now we're going to do a little activity. And it's let's support a launch. And we're going to use, when we are supporting a launch, we first of all, we don't call each other by their names. We don't say you're on console, you got this launch team all over the Earth. We don't say, "Hey Mary, how does this rocket engine look?" And there's a problem with that. First, there may be a lot of Marys, and also it doesn't say what Mary really does. What is her function? So instead, first thing we do is we assign everybody that works on a rocket launch has a purpose. My purpose is to work on the first stage engine. Your purpose is to work on the avionics. This person's purpose is to work on the propulsion system. This person's purpose is to work on structures. So that's your name. That's your new name, structures. When I communicate with you, I don't call you Mary. I say, if you're supporting first stage propulsion, I'll say first stage propulsion. and I happen to be the launch conductor, I will always say who I am. First stage propulsion. This is the launch conductor. And then I will ask my question. And that's very, very important. We can't have people blurting out, hey, Joe, how's everything looking? So that we want to be able to follow who you're talking to and who you are. And again, you're using what we call call signs. And the call sign is just what your function is, whether you're responsible for structures, the propulsion, the engine, the other, what engine, hydraulics, and so on. And also, you see those radio protocol pro words. We want to use those, and those just to really avoid misunderstandings. And you see the top one, affirmative, which just means yes. And if I say how are things looking, and you say, I said, is everything look like it's going to work okay? And you say yes. There's a little bit static on the line. I might have thought you said guess or west or test or yes is things can get if you say it quickly, I may not understand that. So instead of saying yes, it's much more clearer to say that's affirmative, and that means yes, but there's not going to be a lot of misunderstandings. So right there are some of the things. Break. That's what we say to break up a conversation if you have an urgent message to tell. So someone is rambling on about a problem and you want to speak, you say break, and then you say what you say. You can say a couple of the other ones. Then instead of no, you say negative. And again, what rhymes with, there's so many words that rhyme with no. You could think he said go, low, toe. I don't know why they would say toe, but they could say a lot of things that rhyme with no. So we want, instead of saying no, we want to say negative. We also have the military alphabet to the right. And we use that when we have to translate codes. If I have to say the code is A, B, Y, Z. And people might say, what did he say? Did he say A, C, D, Z? Or what did he say? What was the code? And instead of saying A, B, Y, Z, I'll say Alpha, Bravo, Yankee, Zulu. And there they understand, they can say, okay, he said Alpha, Bravo, Yankee, Zulu. And the A in Alpha stands for the A, Bravo stands for the B, Yankee starts with the Y, and Zulu is for the Z. So we try to use the military alphabet. So we're going to do a little exercise right now, and everyone's going to participate in this, and we're going to do a simulated launch. And let's go ahead and run it.
So I'll hop in here, John, the teacher, Kelsey. I don't know if you're able to give the numbers out or if you want to do that right now, and then we'll go over the instructions quickly. Awesome.
Okay. So like quadrant right here. Hey, you guys might not are gonna be one. Hold up one. Don't forget all the way to all. Now you just say this front square for 3, 2, hold up 2.
All right. So remember your numbers, and we're going to be asking you, what is your launch code? And you will say, launch conductor, my launch code is, and you'll read off the code on the screen. And then we will ask if you're go for launch, and you will say affirmative. So we're going to do a practice run all together here with you all and the people on the meeting. So I'm going to go ahead and ask.
Hey, Lauren, can I make one correction? First, we should actually ask. Actually ask guidance or whoever the call sign is. This is the launch conductor. What is your launch code?
Yes, that's what we'll be asking.
Okay, good.
So we're going to do a quick run through with everyone here on the call, and if you want to join in the room. So I'll be asking avionics. This is the launch conductor. What is your launch code?
Launch conductor. This is avionics. My launch code is Foxtrot, Oscar, Yankee, Delta.
Avionics, are you go for launch?
Launch conductor. Affirmative.
All right, so now we're going to go on to our group one. Group one, if you can stand up, you will all be guidance.
Just group one. Listen for instructions.
Guidance. This is the launch conductor. What is your launch code?
Whiskey.
Guidance. Are you go for launch? All right, thank you so much, Guidance. You can sit down. Our twos. Structures. This is the launch conductor. What is your launch code? Structures. This is the launch conductor. Are you go for launch? Great job. All right, now we're on to number 3. Propulsion. This is the launch conductor. What is your launch code? Propulsion. This is the launch conductor. Are you go for launch?
I can't hear you. Still can't hear you. Still so quiet. 4, can y'all be louder? Yeah? Okay, stand up.
Let's see how 4 does. Maybe they'll be the loudest.
All right, winds. This is the launch conductor. What is your launch code? All right, winds. This is the launch conductor. Are you go for launch?
There we go. Thank you, launch conductor. And there goes our launch. And one thing about a launch, we got a lot of different, there's not one person responsible for every system. It takes hundreds of people to be responsible for, they're monitoring the weather, they're looking at engines. And so it really does take a team, a lot of teamwork. And everybody has to be a go for launch. We all have to answer affirmative. If there's one person, let's say it's guidance, our structures, our winds, is a no-go, that's a negative, we won't have the launch. Just one of the call signs, we could scrub the whole launch for the day and try to figure out what happened. So, but in your case, you guys did wonderful. Now, can I open it up for questions? We have some time?
Yeah,
so
we have time.
Okay.
Three.
Okay. I think we got a few minutes. Anyone have any
Okay.
questions?
well,
All right.
Kelsey, just really quick before we get to questions.
Okay.
How much time
Oh.
do y'all have? I'm happy to stay on for. I do know Leanne. I believe needs to leave. Did you want to say anything before you head out, Leanne? Any last words for? Okay, cool.
No, this
Uh,
was a great class, Miss Baldwin. You have excellent students, and make sure, I hope all those kids give a big round of applause for Miss Baldwin for putting this together. It's a lot of work for her. Let her know you really appreciate it by thanking her today. And thank you so much, Carlos, for having us.
Of course, yeah.
Thank
And
you.
Miss Baldwin, did you say there's a certain amount of time that you had? Of course, we'd like to get a
Yeah, we
couple
have
of.
a couple minutes, so maybe we
Okay,
can do
a couple minutes.
Okay.
Yeah. Okay,
Yeah,
that
just
sounds
a few
great.
questions.
Yeah, that'd be
All
great.
right.
Okay.
No? Okay, Ari. And Jen. And
A lot of questions.
Yeah, I bet they do.
Jen and Ari, y'all come. Okay. Ari, you ask your question first.
How long does it take to make one rocket?
How long does it take to, I'm sorry, I didn't hear the last part.
How long does it take to make one rocket?
Oh, how long does it take to make one rocket? Okay, if it's a brand new rocket and we've never built it before, probably about 5 or 6 years. And we have to design it. It's a long time. Now, if we've already built it, if we've already designed it, and we just need to put it together, oh, probably about 9 months. We can do it very quickly. But that's one thing we're trying to even accelerate how quickly we can do it. We're trying to get that down to about 2 months to build a rocket. And there's a lot of parts, and everything has to be right. But that's a great question. Yes.
What else can you do in NASA?
What else can you do at NASA? Okay, well, like I said, we have a lot. They work on a lot of different space programs. We have, they are right now working on the manned spacecraft. We want to go to the moon. We have not been to the moon since the early 70s. And so that's one of the big things they do at NASA is the manned missions where they actually put astronauts on top of these rockets and they go the space station. They're first they're going to go to the space station, but eventually we're going to go to the moon. And we also have unmanned rockets, and that's we have robotic missions to Mars where they have a lander, and there it's all robotics. There's no human being. Right now we don't have the technology yet to go to the Mars. So we send NASA's in charge of sending robotic missions to the various planets, and we actually had a couple landers on Mars. So yeah, NASA does a lot of really really cool things.
All right, one more.
Okay.
Get a little bit closer. What does winds do?
What does winds do? Oh, that's a great question. That is an outstanding question. We're very concerned about upper atmospheric winds. These are winds that may not be on the ground. In fact, it might be a great day. You don't feel any wind, but up there, 10,000 feet up, 20,000 feet up, the winds might be really hard, and it'll break a rocket in half. So we measure the winds. We send up what we call weather balloons. We measure the winds, what they are in the upper atmosphere, and we make sure our rocket, the winds aren't so strong that they're going to break this rocket in half. And the rocket looks really, I mean, it looks really sturdy, but it's not. We want to make it as light as possible. So there's going to be a lot of times that some of the materials can't handle everything. So anyway, that's an excellent question.
Thank you. Okay, that was it for our questions. Thank you so
Okay.
much.
Oh, you're welcome. And again, a lot of hard work, and you're going to be in the space program.
Cool. And then yeah, with
Great.
that, I'll pass it
Yeah.
over to Wayne if you'd like to say anything to help close us out for the day as well.
Well, I just
Okay.
want to say, in the spirit of things, speaking of teamwork, what a great team effort it was today, leading off with our star students and teachers at Montgomery Elementary School. Thank you, students, and thank you, teachers at Montgomery Elementary School. Without you, this wouldn't have happened. And without any of the other folks on the team from Aerospace Corporation, thank you so much, Aerospace Corporation, for your support as always. And Mr. Binkley, this was absolutely a spectacular presentation. It was just great, and thank you so much. You get a gold star. I don't know if they give gold stars anymore in school, but I got them when I was in elementary school. And Carlos, again, thank you for all your support, and thank you for your great moderating. So, and Miss Baldwin, we just can't thank you enough for pulling this together. Just a wonderful show. I hope everyone enjoyed it. And with that, I'll just say thank you on behalf of D. Howard International for the team's effort, and hope to do this again at some point in the future. Carlos, do you have anything to add?
Yeah, I won't throw anything out. I'm gonna pass it one more time back to John Blinky if he'd like to offer any advice, words of wisdom, encouragement to the students, and
Yeah.
then we'll wrap up from there.
Okay. Yeah.
Yeah.
First, it was my pleasure, and thank you for the kind words. But it was my pleasure doing this. Miss Baldwin, you got a wonderful class, and I just want to encourage the students to work hard because that's really is the key, and try to stay focused as you can in class, and that's it. You guys are wonderful. A lot of great questions and great audience. Thank you very much.
What do we say?
I think they're screaming thank you just for
Okay.
All right, thank you all.
Thank
Bye.
you all.
All right.